Yeah. Share with people. Yeah. Thank you.
All set? Okay, great. Okay, so this IA Wind Group, so it's an international research collaboration between 17 countries, this task 25. And we come and share what is happening in each of the countries regarding studies we make with wind and solar, how they impact power systems, and then also experience from system operators, what has happened or how has it gone. And then we try to filter all this information into advice and recommendations on how you should do these studies when you try to simulate wind and solar in your power and energy system in different simulation tools. So how should you take them into account and best ways to do that? We tended, I mean, we used to have a lot of wind and solar integration studies. Perhaps they are not called that anymore. So just think about generally that you're simulating power systems, you put their wind and solar, and here are some recommendations on how to do that. So I will go through this report that is almost ready to be published. Hopefully we'll have it online next week. And the contents is, well, I start with an introduction about the report, and then I go through the recommendations for different parts, for input data, adequacy, operational impacts, and stability. And finally, how to analyze, present the results, and then summarize. So first of all, this report. So the idea is that we would provide research institutes, consultants, system operators, well, academia, of course, with the best available information on how to perform an integration study or how to study wind and solar in power systems. Now, you can basically use this as sort of getting advice, but also if you already made a study, and you're sort of presenting your results and you're writing the part of the discussion part that, you know, what did you take into account and what you didn't take into account. So these could also be used as sort of checklists that you could basically refer to this, that based on their checklist, this is what I did take into account and this is what I didn't. And then this report is only about methodology, input data, but we do also provide reports on the actual results that and experience from different countries. That's just another type of report on our webpage available similarly as this recommendations report. And we have done, so this is a recommended practice report number 16 of IA Wind, and this is edition 3. So we already did this 2 times before. When we did this the first time, more than 10 years ago, it was, you know, the shares of wind and solar that was studied at that time was about 10 to 20%. So that was the first recommendations. And then we only looked at wind. When we made edition 2, then we added also solar. And with solar, also a short section on distribution networks, because normally we only look at the system-wide simulation, so the transmission. And then we had the recommendations that, okay, if you only study your first small shares of wind and solar, how to do that. And then if you have more, then you have to additionally take into account this and that. So that was the report, the edition 2. Now for the edition 3, we add a third layer. So for wind and solar dominated systems, really high shares of wind and solar, then what you need to take into account. And we have gone through the report and updated all the texts. And this is the flow chart. For the previous editions, it was actually more complicated. So this is a bit simpler way that we try to present this. So first you have your scenario, a power or energy system design. And then you go through 3 checks with simulations on the operational impacts, on the resource adequacy, and on the dynamics. And then you check, is your scenario feasible, or do you need to modify something about your inputs or your assumptions, or generally about the scenario? Whether you need to add more transmission capacity, you need to add more storage, add more generation, add more flexibility. So then you need this iterative idea, and then you have a scenario that is okay with the feasibility checks, and then you analyze and present your results.
Excuse me, what do
Yes.
you mean by a scenario? Because we use that word in very different contexts. What is a scenario?
So basically, you could, yes, it is the power system that you study. So you could have like 2 scenarios, like less wind and solar and more wind and solar.
The portfolio of infrastructure.
Yeah, it could be a portfolio of your generation. Yeah, I show it with it. I have a
So the
Maybe I
scenario
have a
could
slide.
also include, for example, realizations of uncertainty of some wind or solar. It could also include certain kind of contingency. So that you're not including in this. Those are separate.
They are in the middle part, so.
Okay.
So it's the main, sorry, Andrew, can I?
Yeah, yeah.
So the main scenarios would be, I'm gonna have 10 gigawatts of wind and 4 of solar, sort of
let's see.
broad scenarios if
I
you
see.
want. And I might have wind and nuclear, or, you know, so there's sort of the big picture. When you come down to some of the boxes in between, you
Yeah.
know, operation, you may well have, you know, uncertainty represented.
I
and You
see.
may well have sort of
Good.
scenarios appearing.
Okay.
So it's just different.
That
you're-
helps.
Yeah, yeah.
Thank you.
yeah.
It would be even like broader than that, so it's like that megawatt of solar comes out of assumptions of I'm gonna have an emission policy like this, and then
Yeah.
the cost of equipment is gonna
Right.
be like that. And that will come up with a certain scenario of solar, wind, and other generation, and that's what scenario would be.
So I have only this slide about this. I have a sort of zoomed in flow chart, but sorry, I didn't take it here. That would use that you have all kinds of input data going in. And then also this generation mix, fuel prices, load projection, transmission, and also assumptions about how the generation will work, like their flexibility assumptions is the most critical one. And basically you can either have it by, if you're just studying a current system or how it's going to be over the next couple of years, you can just, you know, take it how it is now and just do a little tweak of how it is after 2 years or so. But normally when you study future systems, you would use capacity expansion tool to optimize
Yes.
this scenario that you have. Okay. So I have a couple of slides of what has changed in 5 years. I think it's about 6 years when we made the last edition. So we did mention energy system coupling already then, but just very lightly. And now it's like really quite in the center of things. That when you start simulating your future power system, you need to have links to other system couplings. You need to have somehow, you will have electric vehicles. There you will have direct electrification options that you see directly in your power system, but you also somehow should take into account the indirect electrification, like power to heat with heat storages, power to hydrogen, e-fuels, hydrogen derivatives, chemicals, ammonia, whatever, with the storage buffer possibilities there. Because when you have more wind and solar, you have more variability. So the flexibility is something that you always have to keep in mind. Do I have all the flexibility options modeled? And not overestimate it, but also not underestimate it. Somehow you should have all these in your model taken into account. So it's it's really a bigger picture. Even if we have a power system focus, the links will be seen in power systems through flexibility. For example, in Finland, you have district heating systems, and they used to be provided by combined heat and power plants burning coal, and now they are building electric boilers and heat pumps, and they have a weekly large thermal storage, converting oil cavern to a thermal storage. So you can see it's more, there will be a electricity demand with the weekly flexibility. And of course, you need to have that in your power system model somehow. So it's really changing. A lot of new things are coming and changing. And this is an example that I found from Denmark, system operator Energinet. They have future load projection that they made 2 years ago, all the way to 2050. And then they have the current fixed demand and partly flexible demand in yellow. And then when they start looking at what new demand will come, all this is potentially flexible. So this will make a huge impact in when you start looking at what's the impact of wind and solar to systems. If you model this flexibility there, it will be a different result. Of course, we don't really know how this will come out, but just, you know, recommendation, try to at least take a sensitivity of the possibilities and options coming there.
You consider also, or maybe you have.
No, go ahead, please.
You consider also the coupling with the natural gas infrastructure from this transmission pipelines, but also like supply risk would be for like extreme weather events, induced disruptions, or geopolitical.
You can
Supply flows.
include whatever you like in these studies. It's up to your study to include as much as possible of all these things, and then report, when you report your results, report that I did take this into account or I didn't.
Okay, and has it been done by the IEA already, or
No.
no?
Yeah, there are studies that are looking about optimization of the hydrogen network and transmission network with future generation mix options. These studies are currently being made.
Can I ask?
No final result, I would say. I would not yet trust very much the first results that you get, but I mean, this is a very, very good topic. And then of course, when you do these studies, also including more detail of the gas network.
So just going back to scenario question. So let's say I like this scenario, it has so much flexibility. That flexibility is going to change over time, over long period of time as you go, and it's going to have an impact on actual composition of what's flexible, what's not. That's very hard to take into consideration. Do you think about that or not?
Yeah, then you would probably make studies for different years.
But it has to have this feedback which says, okay, because of flexibility now my inelastic demand reduces, and because of that prices came down, and because of that I need less hydrogen. So that emulation of that, we do that in operations, you know, for shorter term, but for the longer term, I think it has huge impact, and I don't know if it's done.
Because there are these long-term planning models that really look at the whole energy sector, like what we use in Europe, times, and IEA uses also times. But I have to say that the power system part of those models is very rough, but not very detailed. It's not chronological, it's time slices. So always when you hear time slice model and you're looking at impacts of wind and solar, then it's like, okay, we get some annual indicative results, but we need to go more in detail in the models to really see whether it works. So you often start with this sort of policy market planning, long-term modeling, where you can, what is nice, you can include also other energy sectors, what's happening there. And then you would go more into detail in the power system techno-economic plant performance, unit commitment, economic dispatch. You would actually run the operational year or many years, and then you would go more into detail in your transmission network, look at the power flows, and then finally also check the stability. And basically, often it is done in some studies all the way down to system stability, and the system operators need to do this.
This helps me ask the question. It really goes just one. That's what I wanted to
Yes,
ask.
yes,
Sorry.
so indeed, red ones, we don't see much.
Yes, that was my question. Okay.
And it could, of course, be, I mean, also you, but these red ones is what we should start
Yes,
seeing more.
okay, done.
Yeah.
So are there some specific examples where the red one is done that you are aware of? Because this is something that we are, this is a very nice slide and
Yes.
what we are interested, because as Maria is saying, there's some kind of endogeneity in terms of when you go from one level to another, how to sort of get the information from the lower level to feed back into an upper level. That is the key kind of question which we are facing across different levels. So are there specific studies that you recommend which does that already or tries to do that?
You should do more work.
Well,
I know, but
there are
somebody else has done.
there are papers and studies, for example, trying to get some constraints out of system stability studies to the unit commitment and economic dispatch, that you add some constraints
That I can
that you
understand, but
get.
for planning, are you familiar with something?
But then for planning,
For the big red arrows,
Yeah,
big red
yeah.
arrows.
Yeah, so like what Hannele is talking about, so say, my examples are all from ERPA because I've worked there for 10 years. So gradually they started picking up. So this stability constraints are pretty big and limiting and bind over a long time. So now they run certain like snapshots. It's not ideal, it's not very scientific, but they run certain snapshots and they take the stability constraints, I believe now all the way to even generation expansion model. Yeah, it's still not perfect, and this is not like for every year and for every case that they will evaluate how it like changes over time. But crudely, they take some stability constraints into generation expansion because it affects where new generators are
And
being.
our court has reports on what you're just saying.
I
Yeah, there
believe
is
so.
some.
Okay.
Can I comment? So I
Long-term
think
planning.
your slide indicates that each box is one model, basically. At least that's how I read it. Do you see that, could some of these boxes be merged into one model?
there has been a lot of talk about this, that you take, for example, that you take this unit commitment and economic dispatch more and more when you make your capacity expansion. So the models are sort of, perhaps the detail is not all the detail, but sort of more and more this planning and operational time scales are merging, and with the computational capacity that it will enable this to happen more and more. Would you have, Mark, something to say on this?
Yeah, but I mean, is it worth doing? I mean, I think that's just a sort of. Nick Miller has a good thing to say. Nick Miller's from GE, and Nick Miller told me that 20 years ago they was in GE, they had the same, like, let's put one model to rule them all.
Yeah.
And it's just a, it's a nightmare to put it together.
Oh,
And
it
then once you
is.
get out of it, and at the same time, it's just a model at the end of the day, and how much error is in this model? So is it really worth it?
It depends.
I definitely think that some of these, the simplest example I know of something down here, system stability going into the planning models is the inertia constraint. And that's been done several times.
That's simple.
Because it's simple. So there are some that you can put in, but I wouldn't put in huge numbers because why? You're getting this huge amount of detail, but I mean, the errors in this are enormous. The data is wrong, the models are wrong.
But I think like where there is an area of like where it's headed right now, so in my mind is more of like this errors. It's not like you're trying to put everything within the same model, but more work on the process and how data is organized so that this data is easily transferable from one process all the way down. And you can like grab whatever data set of the entire data set that you need, but it's one single data set. That's very important. And also how the output flows into the models and how you do feedback.
Actually, for some of us, sorry for speaking too much, but you were talking about there is in ERCOT, there is this really harsh stability constraint and reduces how much you can transfer wind and all that stuff. Some of us work on very fast time scale when you can actually change the automation on the power grid. So that constraint goes away. The potential benefit of that is not understood at all.
Yes.
I just, there are no studies of that because when we go, as we go from more coarse models down to lower, we actually keep the lower ones as really hard constraints. They can be relaxed with different technologies / flexibility, but with automation, I know I work in power grids. These system stability things are just so limiting and they can be with very little, control, and there are people who work on this, relax so that you can, not spill wind and stuff like that. I think there's very little work on that, unfortunately. It's more on analysis. So this is more analysis, so the question in your thing is, who decides what to change as you go back? Is that like operators do or planners, or it's because they think it would be so, or are there some rigorous tools to do that? Anyway, sorry.
It's like operators and planners
Yeah.
these days. I would say.
But
And I mean, when you do research, you want to take everything into account as
So,
best you can with your resources.
so Maria, I'll say two things. So Maria, there's within NISO and GPST, there's a project been done on topology optimization in this.
yes, and
Yeah,
you can
no,
do
no, yeah,
ACOPF and
yeah.
different things.
I know, but you mean the topology optimization problem itself is, it's at least a 10, it's at least a, what is it, a 10 to the 18 combinatorial problem with AC. So it itself is a nightmare. So, but there are people working on that. But I think also to say, so the Gates, Breakthrough Energy or Gates Foundation want to put a large amount of money into this space. At least this is their intention. They announced it essentially.
Into errors. They said, we want to, initially, they said we wanted to put it into one big tool.
Yeah.
But now we realized we need to
Yeah.
invest in this arrows
right,
that
yeah.
come back.
Yeah.
But in the
That's
process.
the point,
I
yeah.
mean.
So,
But
so
you
they're-
say it's a process, really.
Yes.
So they are investing in methodological gaps? You're
No,
saying that
no,
they're
No
interested?
process.
No, they are going to invest in trying to integrate all these tools together, not in one big tool, but in maybe conversion tools,
Yes.
common data sets.
Data
And that's probably a
massaging
much
tools,
more
yeah.
valid way of doing
But
it.
just since you're speaking about this, in terms of actually putting things together and how information and data
Yeah.
flows across these
Yes.
things, there needs to be some systematic thinking in terms
Yes.
of how errors propagate, what is the influence?
Yes.
What is the result of
Yes.
the output, right? So is there some thinking about this?
Yeah, I think so.
Okay.
They haven't come
That's
out with the detail,
interesting.
but that's a much more valuable thing to do. Because if you create one model, right? There's no innovation in that, if Alden comes up with a new capacity expansion, whatever, how do you fit that into but if you have an environment in which you can add things together, it allows innovation to go on and allows different areas to progress. So I do not believe one model is the way to go. I believe having an environment within which models can all fit in the same
Yes.
environment, trade data, common data platforms, and the thing about errors and all the rest. So I think that's the way to do it. So
And anyway, then this one model to rule them all will go to Mordor and we
yeah,
are
that's right.
doomed.
Yeah, exactly.
Yeah, one thing to also think about, and maybe like for research community, very important, is there is this, like, how do you call it? Like industry inertia. So I mean, everybody is already set with the tools they already have,
Yeah,
and the
yeah.
tools are maybe good for like each one of these boxes. And people don't want to like give away with these tools to jump on a new shiny
Yeah.
thing that rules it all. but,
Everybody
like,
wants to make their own tool more
Yeah, yeah,
popular.
yeah, but like automation between the tools that people are already familiar and happy with for each single process, that's something that's important. And like data flows.
Judy, my talk here last Friday was on that. It said power systems inertia and inertia in power systems research. Exactly.
Yes.
But I mean, also, if you make some really future studies and you just do the techno-economic plant performance and unit commitment and you don't do anything else, this is actually, you're just assuming that in future there will not come constraints from there.
Yeah.
So it's your first approach. You just assume. I mean, I think many of these 100% renewable studies, this is what they do. They just assume that when we get there, they have solved all these boxes. But I mean, of course, it's different studies do different things. But what would be nice would be that they would be transparent, saying that, okay, we checked this or we didn't check this, and so on.
I think it also depends what kind of decisions you're taking based on the studies, right? So if you sort of long-term planning study, the idea is to find maybe like transmission projects that over longer term, like they're very large scale and over longer term make sense. But this like very big, very long-term studies, maybe what decision you're looking for is some kind of policy decision for, should I like have some renewable goals or should I have some, changes to the.
Yeah, that's right. The studies
economic
are very
assumptions
different.
and-
Also, the research questions are very different, and then you need different detail.
Or in academia, the objective is to get a paper published, which is completely.
Not, not for all.
I'm just saying,
Students.
I'm
For
just-
students, it's important.
Yeah, for
I
non
said this last Friday, you and I. can
Okay,
sit up
Mark,
here-
stop. here. So we tried to make summaries of all these recommendations, and for input data, we summarized it is this one monster table where you have all the different model tools, and then you have, okay, how you should have wind and solar there. So PV is photovoltaic solar, how you have their forecast, how you have load and load forecast, your network and other power plants. I just zoomed in here, like just to show one that for the resource adequacy, or if you're wanting to calculate capacity value of wind or solar, then okay, you need this hourly time series, at least, well, hourly usually, that should be representative. And time synchronous with load data, and then you should have 30 plus years if you really want to capture your resource adequacy. You don't use forecasts, and for network, you somehow model your neighbors, so that if you take this into account with your cross-border capacity or interconnector, then you also need to check that there's also a forced outage rate there. And for other power plants, you would really need their forced outage rates, because the resource adequacy, loss of load probability, that's dependent on that. So just to go through one of these columns more in detail, and the note that we have added is that when you have this long time series of wind and solar, and if you're not just simulating a case for today, you should think about climate change impact to any weather dependent data that you have. However, we know that there are caveats in current climate model data. So you have to be a bit careful that if you just take the data for wind and solar from a climate model, maybe you are adding actually even more uncertainty than what the climate change thing is. So you shouldn't only go for the climate change data. You should also check with the best simulations you have.
Are there like public data sets out there based on climate models that you're aware of?
It's actually what in Europe, all the system operators have this NSOE, and they do the transmission planning and resource adequacy checks for all of Europe. And they use data sets that are public. And at the moment, they have it based on historic data, but they are, so it's DTU in Denmark who is doing these data sets for them. And they have already made also these climate change data sets. And I'm not sure whether they are public yet, because they just made public the data sets that they use for Europe from historical data. So this is something that is coming. And I'm not sure, NREL is doing also some data sets.
NREL is doing data sets. The thing is, it's oftentimes, and in Europe is better than here, but oftentimes people that concentrate on climate change models, they somehow like don't have access to or don't take into account the like very good correlated data sets from historic data. So like there are people that concentrate on historic data sets and how to use it in a shorter term planning. And then there are people that are focused on climate models and somehow they don't talk to each other. Yeah, we have at ESIG, I will not be able to cite any studies, but if you're interested at ESIG, we just published maybe about a year ago, a report on importance of weather data sets and what kind of correlations matter and like how far in the past you need to go, resolution, all of that. And so it discusses all different available data sets, both in Europe and in the US, and kind of identifies gaps in there. So I can share if anyone of you is focusing on this.
And another important note that we want to highlight here is that the technology has improved a lot, or sort of, improved, because the capacity factors that used to be between 20 and 30% are now, so the average power coming out of wind power plants used to be between 20 and 30% of installed capacity, and now it's between 30 and 50%. Because they use longer blades for the same generator. And of course, when you have wind speed data and you convert it to power production, you really want to then use some relevant technology data to do that. And of course, solar data, so the solar panels, they are also improving. What's the average power coming out of it? So these things you need to check. And of course, you have existing capacity depending on the year that you're studying. You have the existing capacity and you have that already perhaps from your historical data. But when you start looking more into future, you really need to also take that into account. Okay,
Just one thing I kind of noticed, maybe we need to add to this, like when the weather data sets previously, when we thought about it, you primarily think wind, solar, and load impacts, right? But now we also notice, especially with more extreme weather, that it has impact on generation outage, both like wind and solar and hydro, but also thermal generation outage. Whereas before, saying resource adequacy, thermal generation is assumed 100% available, and this like impacts of weather are not taken into account.
Yeah, I
And
have that
same
in
on
the resource adequacy. Yeah.
Just ask a quick question. It doesn't have to be a long answer, but if you go just back 2 slides, are there any sort of, do you have any idea of which parts of these are related to storage, or where storage exactly comes in as very important? And also, are some of these more sensitive to the models than others? Is there an answer to this question?
No, this covers so many different tools and data that I can't say anything general. We don't have specific recommendations for storage data. It's,
I would say it's like active area of research still how to consider storage on this more longer time frame, because it's like, I mean, if we meaning like lithium ion battery type of storage,
Yes.
because it's something that dispatch just a short term, and how to consider it for resource adequacy. And
Because in certain countries, you see, the solution to more intermittent renewables would be storage, not necessarily tying it to other countries, to neighbors around you. In certain countries in the world, that would be the only option if they want to decarbonize as faster as you want.
yeah, you could add peakers or storage or demand flexibility or transmission. And every case study would have a different combination of these two, and sensitivities of these 4 would be a good idea to check. Because for the demand flexibility in future, we know the potential is there, but how much will actually happen, we can't be sure. So making sensitivities would be useful.
And I think it's fair to say that our resource adequacy is extremely sensitive, because so the one aspect of this that's very.
Yeah, let's go to resource adequacy, and then because it comes, it really comes there.
When it comes to adequacy. The rest of it is probably.
Just shortly before we go to resource adequacy, there is something about scenarios. Yeah, as a summary, okay, if you have small amounts, if you're just looking small amounts of wind and solar, you just look short term. So it's okay, you just add to existing or foreseen system. Just keep it as is. But as soon as you start having larger shares, you need to look at the changes that is happening in the sort of the remaining system of wind and solar, and then capacity expansion tools are becoming recommended. And of course, if you look in a future wind and solar dominated system, you must study or make your scenarios with capacity expansion tools. But also these tools should be improved. So they should have demand and storage included, because many of the tools now don't really look at that in detail, the future storage or the future demand flexibility coming from decarbonization and electrification. And also some of the capacity expansion tools don't really look more in detail in the short-term balancing, but once you start having more wind and solar, you should have a tool that is chronological, that you can see the variability, and also the grid constraints there should be modeled. And regarding markets, it is a recommendation that that it's a good idea to study different options for future operational practices. Okay, so then going for the first check, whether your scenario that you have built is feasible. So I've taken now as a first check this box in the middle, resource adequacy, and there it is. Well, resource adequacy is a lot about having enough generation and storage. But then also the network adequacy could be here for the transmission grid and for the distribution grid, to check also that, do I have enough transmission and distribution built? And here, what we have seen already from all the studies, that how you model your neighboring countries, that's very important. So all the possibilities to exchange, import and export, that is important. And for resource adequacy, especially the import possibilities during times of generation scarcity. And how this is done, it's quite difficult with old tools. So these sort of model developments actually using sort of simulating hour by hour and using Monte Carlo for all the outages is the best way we know that we can to do this. There is considerable interannual resource variability, so you need longer time series. Sometimes there was a study just looking at Ireland and checking that if we only take 1 year or 2 years, but we take different years, we start, first we had the results all over the place. But once we had about 10 years for Ireland, then Ireland and only wind, then we started having that whether we chose it differently, the results started to be similar. But after that, looking at case of Finland, case of France, it was quite clear that you have benefits when you have more than 10 years of data, and 30 plus years is what is recommended and often done nowadays. And then, of course, it's not just that you have installed capacity enough, it's generally energy becomes more. You need to look at the energy. So it's not just the peak load in megawatts and how much you have installed capacity, but it's, how the energy scarcity happens, on what time of year that happens and how it happens, and maybe it's no longer a single or a couple of peak load areas, peak load hours that are important to look at.
So can I just ask?
Yeah.
If you just adapt 30 plus thinking, that you really have to know everything for 30 plus years before you do anything. I think that uncertainties over different time horizons are so uncertain, right? That actually maybe a better process would be over, have a stratum of decisions, for 30 years, I can decide on very large
This
scale.
is different. This is different.
You just
I
said,
think,
yeah?
yeah. So this is that you are simulating a certain year that can be this year or next year. or 2 years from now, or 10 years from now, but you take 30 different weather years to simulate.
But
that
I don't
year.
know what they are going to be anyway. So I
Yeah, that's
think
what-
Yeah,
you,
but you have all this data available.
from where?
Well, in Europe and US, you have.
But those data are very hard to support, right? 30 years from now,
No, it's not 30 years from now, it's 30 years of historic weather.
Yeah,
And so you pick weather, so let's say some weather years have more probability than others based on.
and how it's going
statistics
to
and-
change for the next 10 years, nobody
Yeah,
knows.
so that's where climate models come in, and so they model how this 30 years of weather data can potentially be affected.
I
by
guess
climate
my big
change.
point was, as we are going to have this process, of not having one single model, but having different levels of granularity for different uncertainties, we really should be thinking about distributed risks over different spatial things and different temporal, rather than just doing one thing, that answers everything.
Yeah, but in order to quantify this risk, I think the point is that this historical 30 samples or 30 years might be a good way to sort of try to assess the uncertainty in quantifying that risk.
Historic uncertainty.
Yeah.
Yeah, but I'm returning more to Julia's process thing, rather than just having one model.
Yeah,
That makes
sure.
no sense. I think what's happening is that you need different levels over different times, different,
but this is only
spaces.
to do with resource adequacy. This is
Resource
on-
adequacy.
Yeah, this is, now we're talking only about resource adequacy. How are you making sure that you have enough capacity and storage in your power system for this amount of wind and solar that you're
But it's going
studying?
to depend very much of what I did before now and when I need that equipment. So this process is interdependent, I think. So it cannot be just for research adequacy, just for that, because they all affect each other. Cumulative effect of what I did now in the shorter period of time should affect how much I
This is
build.
how you, so now we are thinking that you have a research or a planning question about a certain scenario. And then you probably need to study, even previously, you needed to study several different scenarios for your future. If you're looking like 10 years ahead, you would have like 4 different scenarios. And now I think you need to much more scenarios or sensitivities to certain scenarios to capture all the uncertainty. But this is okay. This is more, I see it in this construct, in this report, I see it as a sort of scenario setting thing.
Okay.
And how many scenarios you need to study. But then when you're studying one scenario and you want to check if that scenario is adequate, has resource adequacy, then you try to capture the weather uncertainty by using 30 plus different weather years. And hopefully in future, we can do this with climate change impacts included. Now I'm just saying that we are starting to do it, but there is much more uncertainty in the climate model data than the historic.
That's good, yeah.
One just a time check.
Ah,
We have to
okay.
be a bit selective, I think. Some of us can probably stay stick around a little bit longer, but some people have to leave.
So
at,
what about
10% through one speaker and we're.
I'm just showing what I have in the slides and you can check them later. And then we move on to Julia's part. So I'm just having actually here an example how this resource adequacy is made in Europe. And just, there is a full, I'm having here the source, there's a full presentation in the spring ESIG meeting. They have always esig.energy website has all the event presentations available there. So you can go and check how this is actually done if you want to know more in detail how they do it in Europe, because this is quite a nice methodology that they do. We have 27 countries in Europe with interconnectors well meshed. So how do they take into account your neighbors when you do this? So this is a nice example for that, and how they present the results that you have an average of these 30 something weather years, but then you also look at the tail events, one in 20 years, then you get the much higher loss of load probability and what they plan to do in future.
And just one small caveat, so this is the workshop that just happened that we're coming from, so the.
No, this is the spring workshop.
The spring workshop, yeah.
Yep.
So, yeah,
Will you
just,
share this information with us? This.
Yeah, the slide,
okay,
yeah,
good,
the
thank
slide
you.
will be shared. And then there's some recommendations also how to calculate capacity value. And then you can also look at the transmission part with some steady state checks. And here are just some recommendations how you do the steady state checks for the network. Generally, a transmission planning process would have the scenario setting. You would go the operational thing, and then you would go down and check all the way. And then you check, okay, here we need more transmission, and it's a more complicated process, but we just make some checks for, power flow cases to study, how you do steady state security checks, how you do short circuit checks for weak grids. So this was for the resource adequacy part. Then there are some recommendations for the operational impacts, the unit commitment simulations, like this is to ensure that the studied scenario is operable, hour to hour or 15-minute to 15-minute or 5-minute to 5-minute, whatever is your power system, how it's operated. You do it with these unit commitment and economic dispatch tools. And there are different ways you can manage variability with reserves and doing faster scheduling process closer to real time. And then there are some recommendations, how the time series, how you choose these base case scenarios if you want to compare. And then the operational simulations, what you really need to then include, you really need to include everything that impacts the flexibility, because you're simulating more variability in your system, and hopefully also include something for the grid constraints, and also recommendations how you do operating reserves. So just to make sure that with increased levels of wind and solar, you also have increased levels of the reserves that will help to operate the system. And then we come to do it.
how much time do I have? Just give me a ballpark.
I mean, I'd say, if people need to go, you can go, but you can
Yeah.
take 10 minutes.
Takes 10 minutes. Okay, yeah, that's fine. I think I mean there are a lot of recommendations kind of going into specific, like if you are doing the study and what is the specific concern. But I think at high level of things, so like if you're doing integration studies, so I'll just talk from that perspective without digging into details of specific stability studies. What you're looking for is this high level constraints, that scenario that you come up with for generation expansion, and like from your resource adequacy is not feasible in terms of like stability, and it's not like you cannot operate a system like this. And so you need to put some kind, what you're looking for is some kind of constraint to feed back into your generation expansion, so that your generation mix turns out certain way. And generation is being built in certain locations, because like other things, like there are smaller things, like Maria, you're saying that it can be solved in operational realm, and you don't need to worry about them when you're deciding what kind of generation you need to build and where. And so this, I think like what you see here in the slides will be a mix of what matters for stability study on its own, and also like what matters for stability study in the grand scheme of things that you need to take back into this generation expansion and unit commitment models. Right, so yeah, what you're doing there, you're kind of investigating what impacts do you have from the generation mix that the model comes up with, and the impacts of distributed generation. So if in a given model you get a lot of distributed resources, how do you even model that? It can be very small and very many. You need to understand again what impact do they have in the grand scheme of things, but also like operationally. transmission limits. So I think historically it's only, you look at only thermal limits in this higher level models, but now it's more stability constraints become more binding and they are below thermal limits of transmission lines. So basically like, what this means is that like you can transfer more over given transmission line, but because you have certain operational constraints on a cluster of generation, you cannot let them generate more, and that is translated into transmission constraint. And then, yeah, then maybe if you have, so the wind solar storage resources, they're kind of different technology compared to conventional synchronous machine, like big machine that we are used to operate with. So you need to consider if there are any interactions between these resources, if the model builds a lot of this type of generation in a certain area remote from the rest of the grid, there may be control interactions that need to be taken into account. And that can translate again into a dispatch constraint that needs to be fed back into the model. Or maybe you have some other control solutions that you can do operationally and you don't need to worry about it. And so what it kind of means for this big scale planning model or integration models is that you need to understand what kind of cases you need to look at. So previously in this type of studies, you maybe only look at in this smaller scale models, in like stability type of models, you only look at 2 snapshots and a peak case and a winter case maybe. Before it's even like maybe it's just peak case. Gradually it's maybe winter case. Now people also look at shoulder cases because that's maybe where you have a lot of renewables, but maybe load is not as high. Maybe you don't have sufficient amount of large synchronous machines online to provide some of the reliability services that they have been historically providing. So you need to think where do you get this from? And then as you get more and more of this type of resources, system becomes sensitive to how you model these resources. So before, like you had few wind turbines here and there, they maybe don't affect system so much where you need to worry about how these are modeled. But now, as you have a lot of them, modeling becomes more important. I think recently load models are again gaining more interest, and this is something that's overlooked over time because you have less, system operators have less visibility of load models of like types of loads and characteristics of loads and less capability to model this, but now system becomes more sensitive as to how this is modeled. And then from that you choose cases that you would like to study more for like stability impacts, and this kind of list different types of stability that you need to study for, and based on what type of stability you are focusing on, different details matter, and you may also use different type of tools to
Question, please.
solve it. Yes.
So where does the times model lie in our take from this? Does it look at any dynamics at all?
Yeah.
Not whatsoever.
But-
Okay.
Times.
That's
Times.
the long-term planning model with time slices, but it
Ah.
has all energy sectors, but for the power sector, it doesn't.
Yeah.
It doesn't even model the unit commitment of dispatch. So it doesn't go down this,
Yeah.
this,
Yeah. So
Down the lane that we have
Yeah,
just described. Yeah.
yeah.
it stays, that's the first.
Sure.
yeah. And this is the last.
Yeah, this is
That's,
the last.
that's very kind of uncomforting for me, but yeah, go ahead. Go ahead.
But what you're really looking from here is like to get to, like, you're looking to understand stability concerns with a given scenario, but also from that stability concern, you're looking to understand what do I need to do about it? And is it like an operational decision? Is this something that I can do just like this controls tuning of several resources, or do I need to put in like massive constraint back into my planning models that need to build more generation?
So what, I mean, let's say you find a major violation, what does that constraint look like that you send back up?
Yes,
remote
that's
control?
$1 million question. So some of them are, that's why everybody is so focused on this inertia constraint, because some are easier than others. So from inertia perspective is like, you need so much rotating mass. That's how people translate it. You need so much rotating mass. You can translate it into, I need so many synchronous generators committed in a unit commitment model all the time. At any given time, I cannot let less than this amount of synchronous generation online. But this kind of breaks because now there are ways to do it even with like inverter-based resources, there are ways to do it. And so then the question becomes, how do you feed it back? So then you need to reflect, because not only you need to put in a constraint, you need to put in capabilities that before you were not looking in unit commitment. You need to have this characteristic. So say synchronous machine has so much inertia, so you count like if it's online, then it brings so much inertia on, and I have this constraint, do I have enough? But now you also need to model this inverter-based resources that are capable of doing that, translate it into some kind of characteristic that you can put in unit commitment, so it counts towards this constraint. Yeah, so this is all like for you to figure out.
Actually, I just want to mention here at MIT, I teach a course this semester on rethinking principles of modeling and controlling power systems. Maybe we should have offline discussion, because I mean, the question is on the table. You can, as you said, is it transmission line proxy, or do I do something about inertia?
Yeah.
And I think universities have slowed down in that area, I have to say, just taking a step back and rethinking. So we have people here working a little bit on that. You know, how do you take that into consideration when you do longer term planning and stuff?
And the inertia is kind of the simplest of them all, because it's, you can say system wide, or it may be system pocket wide, but say like if you have voltage stability
Yes.
constraint, how do you translate
I
that
was waiting for that.
into like more simple constraint? You have to have like certain combination maybe of resources that you cannot allow to operate together, or you need to change the control parameters on the fly. So then that becomes more complicated. Yes.
This is, I think, a related question, but taking a bit of a step back, you know, as researchers, I think, you know, we can all nod along at all of these recommendations and say, broadly, these are all good things. There's various people in the room who are working on various pieces of them. But I'm curious, when you give this presentation, say, to an operator, what are you able to tell them about the pathway towards these recommendations, and where do you see the landscape of actually achieving some of these things in operation?
Like talking from stability assessment perspective, I would say like you have to separate operational concerns from big planning concerns. So I would say from what you're seeing in operations, so maybe like pre-operations analysis, look for things that that kind of more global and that you can translate into constraints that will, in the planning realm, will bring you a solution that is optimal. And then some of the things like say topology switching, this is something that is kind of on operational time scale, and probably you don't model it back in the, you know, this higher level generation expansion models. It doesn't really affect anything. Yeah, so that's what I would say. And then like, yeah, on the grand scheme of things, like you can take inertia as a simple one. If you're seeing that you're having to keep certain amount of resources, I will not say synchronous generator, a certain amount of resources online to provide you this very fast replacement of megawatts that are maybe lost during like loss of generation or during like disturbance on the grid, then you need to factor it back into type of resources that are being built.
So even if we here talk about operations and stability, this report is about doing studies, doing planning studies.
Yeah.
And it's just that you need to go to these timescales to check that your scenario is feasible. But this is not an operational recommendation.
Okay, yeah, that's a helpful distinction.
Yes, yeah, but that still is a good question to ask. So
Yes.
yeah, that's good. And also, what I just thought that one thing too is there are also several timescales that you can bring into. So like you're seeing some issues in operations, and you can solve it in different ways. You can solve it by requiring future generation to bring this sort of capability. If it's on every you need it from every generator, then it translates into requirements. If you need it from a handful of generators, maybe you need to introduce some kind of incentives in the market, and it's a shorter term decision than like large planning decisions that Hannele was talking about. Yeah,
Thank you.
all right, what do I have here? I think I probably like have this slide, stop on this a little bit more. So this one is more about kind of going back to what Hannele was talking about different types of tools. So we are seeing more need to like tie these tools together. Before, the stability analysis was more kind of a separate thing, and you don't look at it in your like transmission planning exercise or integration study exercise. Now it needs to be more like talking back to each other. And so this one shows kind of tools needs before, and so like instability analysis, this positive sequence, phasor or like phasor domain transient tools were used previously very widely by system operators. These are like well understood and known models are available for types of resources to do this sort of studies. Previously, this electromagnetic transient, so these are what basically like point away simulations, like simulating three-phase system with very small microsecond type of time steps, very detailed. This type of analysis was used for very like specific studies, design studies for equipment, and not so much for like system impact studies. But now gradually, as we get more of inverter-based resources with fast controls, some of the phenomena that happen on this fast time scales cannot be captured in the phasor domain simulations anymore. And so you look at the phasor domain simulation and think everything works fine, because this fastest phenomena are not even represented there. And so then it becomes important to do like EMT studies, but EMT studies computationally super heavy. So there, like active research area is how do you limit the area that you study, how do you model resources in this area, and then how do you translate it back into maybe the constraints into this kind of less resolution type of simulations. And so with that, and because the studies run really long, so it's like, say, a few hundred bus system, one contingency may take like hour and a half to simulate. And you have like thousands of contingencies to check, so that's not practical. And so people looking like at the state space tool, so this is kind of like way over area of my expertise, but I understand people are kind of hitting the system with perturbations of different frequencies and trying to understand where there are resonance points. And from that, focus on these scenarios that showing issues. And so this is kind of like a screening tool that gives me an idea of what should I study in EMT. And then from EMT, it maybe like gives you an idea what kind of scenarios you can focus on in the phasor simulations. So all of this to say, it's like models become more important because you're getting into more detailed models, but if you're into more detailed simulations, but if you have models that are not representative of a resource, then the simulations are garbage and you're waiting hours for nothing. It doesn't give you anything to have more detailed models. And this one, I don't think like I'll go in details. This just lists what kind of modeling phenomena, very high level, what kind of modeling details become important for each type of stability study. Just go
I guess you should wrap up. So if you have any final.
Yeah,
words
I
to
think
this,
I will not like read through this, but basically, yeah, final. I think conclusion from this one, this one shows depending on how much inverter-based resources you have on your system, wind, solar, storage, what kind of phenomena become more important. So some of the phenomena, if you have very little renewables on the grid, you may not study in this large integration studies, but some of the, as you get closer to 100%, then some of these more detailed studies becoming more important. You need to translate it either to constraints that go to higher level models, or you need to come up with different operational strategies of how you're going to handle it, and that, like adaptive controls being one of those. That's also here.
But thanks for all the questions. Much nicer to present like
Mhm.
with questions
I
than
still
with
really-
slides.
It's still recording, Herman.
Hello,